Now comes the semantics part of it. Okay. And to understand semantics, it is always helpful to think about the real world and the computational representation, because there is a dashed line between the two. There is a distinction between the two. The world also has facts. I am not saying the world doesn't have facts, but the facts in the world are probably much more fine-grained than the facts in the representation. A representation is always an approximation of the world. For example, let's say there are 3 people sitting in 2 chairs. They are sharing the chair. Now, how do I represent this in logic? Do I say that both Vishwajit and the next guy, what's your name? Arshiv, are sitting in the same chair, and Arshiv is also sitting in a different chair. So, are multiple facts true for Arshiv? Then it will complicate the assertion that only one person should be sitting in one chair and one person should be sitting in only one chair, and so on and so forth. So, it is going to create hassle. So, in the real physical world, lots of things happen. We are talking at some level, then we go inside, then there is a subatomic level, atomic level, angles and joints and continuous values, and then we make assertions which are approximations, and then we represent those assertions in the computational language. So, we will have to define a term or a representation for actual real world physical phenomenon, and that's called a model also. And often it is said all models are wrong, but some models are useful. This is a very beautiful statement which we will come back to when we talk about Bayesian networks. Anything that you say is going to be wrong. In the real world, exactly that does not happen. But some models will be useful in approximating the real world usefully, and some models will not. And here my use of the word model is like the representation of the world, and not the model in which we think about logic, where there are models for a certain assertion. Some states are consistent and some states are not consistent. There are different terms for model, meanings of model. Okay? So, what is actually happening in that whenever I say P in my computational representation, that is equivalent to some real world fact that Vishwajit is sitting on chair 25. And all these facts have some appropriate representations here, and all sentences in my representation have an associated fact in the real world. And as the associated facts in the real world can imply new facts which I have not explicitly stated, in the very same way the inference procedure will imply new sentences in the representation world. So, we are mimicking, the real world is doing something, we are mimicking that in the representation world. As we make inferences in the representation world, there will be real inferences happening in the actual factual world. And when we go back and forth from the actual physical fact or real world fact to the computational representation, that process is called semantics. What is the actual meaning of this sentence in the actual world that we are modeling? That is called semantics. Okay. So, a simple example of semantics is the interpretation of the possible worlds. So, for example, if I say P and Q, then only the model consistent with P true and Q true would be consistent with P and Q. Whereas, if we say P or Q, only the model consistent with P false and Q false will not be consistent with P or Q. All other models would be consistent with P or Q. So, this is the semantics, that when I make an assertion in the computational world, which kinds of facts in the real world stay. Okay. Now, I will define some more terms. I have to define a few terms before we can get started. So, we have to define these terms called satisfiability, unsatisfiability, valid sentence, and entailed. For example, S is satisfiable if it is true in some world. That means it's a model, it has a model. S is satisfiable if it is true in some world. There exists some assignment of variables such that S is satisfiable. or S is true. S is unsatisfiable if it is false in all the worlds. There does not exist a single world which is consistent with S. There is no model for S. S is valid, or the tautology, if it is true in all possible worlds, if it is always true, if this particular sentence is always true. And then we say that S1 entails S2 if in all the worlds where S1 was true, S2 was also true. Okay. Let's look at some examples. P arrow Q. Is it satisfiable, unsatisfiable, valid, or valid? P arrow Q. Is it satisfiable, unsatisfiable, or tautology? Satisfiable. Because there is some world where P arrow Q is true. For example, P true, Q true. But there is also some world where P arrow Q is false, therefore it is not a tautology. How about R implies not R? This is tricky. Wait, don't be too quick. Is it satisfiable, unsatisfiable, or a tautology? Impressive. It is satisfiable. Why? How is it satisfiable? R is false. If I put R false, you can satisfy this term. R implies not R. For people who didn't understand this, the implication is a syntactic sugar for not and or. So R implies not R becomes not R or not R, which is satisfiable. How about this? S and W and not S. Unsatisfiable. This is not satisfiable in any world, right? How about T or not T? It's a tautology, because either T is true or T is false. So it's a tautology. And last, X implies X. This is also tautology, because if X is false, this is true, and if X is true, this is true. Okay. How about entails? I have to give you an example of entails, right? Let's say my sentence 1 is x greater than or equal to 5, and my sentence 2 is x greater than or equal to 4. Does S1 entail S2? My sentence 1 was x greater than or equal to 5. My sentence 2 is x greater than or equal to 4. Does S1 entail S2? Yes. In every model where x was greater than or equal to 5, x is also greater than or equal to 4. An example in propositional logic. P and Q, does P and Q entail P? Does P and Q entail P? Yes. Does P entail P or Q? Yes. So this is entailment. And on the worlds, real worlds which are consistent with S1, are they also consistent with S2? Then I will also define a little bit of notation. So these three will be the same thing. Whether I use double implication, single implication, or this other symbol for implication, these are equivalent syntactic symbols. However, there are two very important symbols that we need to define. One is the symbol for proves, and one is the symbol for entails. Now notice that entails is a phenomenon about logic, whereas proves is a phenomenon about a specific inference procedure. S1 proves S2 using the procedure IE. IE is short for some inference engine. If the algorithm says S2 from S1. If algorithm can prove S2 from S1. Whereas S1 entails S2, which happens if any world consistent with S1 also has S2 true in it. So one is a property of what is happening in the world in the semantics of logic, and one is a property of what I am able to prove. It is possible that it is true, but I am not able to prove it. If that happens, I will call the algorithm not sound or not complete. Not complete. Whereas if an algorithm proves something which is not true, which is actually not entailed, then I will call that algorithm not sound. So a sound algorithm is one which, whenever it says something, it only says the correct thing. Whenever it says something to be proven, then it is actually entailed in the actual world. Whereas an algorithm is considered complete if whenever something is entailed, it is able to say it, it is able to prove it. So sound and complete algorithm will be all truth and nothing but the truth. Complete algorithm will be all truth, and a sound algorithm will be nothing but the truth. Right. So an algorithm which doesn't open its mouth, is it a sound algorithm or a complete algorithm? It's a sound algorithm. Never says something wrong. Doesn't say anything. An algorithm which says everything is true. Everything is true. That's a complete algorithm, because even the true things are true, but it's not a sound algorithm. Everybody okay with sound and completeness? Soundness and completeness? Okay, good.